CO2 from the gas phase, enters in, as on the operating line here, comes in contact with the liquid to the equilibrium line, and then step back over to the operating line. I recognize, however, that the role of mass transfer is to affect the concentration that I choose on the operating line. In other words, the concentration at the film-liquid interface is what's appropriate, and that's the gas value minus this flux over a rate. That flux over a rate basically shifts the concentration on the operating line to this value over here, and I recognize that the effects of this on the choice of stages for a McCabe-Thiele analysis is as though you shifted the equilibrium line over to get from this point here to this point here, as I've shown here. This means then that this is actually the stage that's used for this, given the effects of mass transfer. And I recognize that mass transfer in general causes more stages than one would expect given no mass transfer effects. Now, some of you may be concerned that this equation that I pulled out of my hat, that rates are given by geometry's famous numbers and a driving force, is not satisfactory. So fine, we'll derive it, and it can be derived relatively quickly. Let's imagine a volume element in space, as shown here on the left, between position z and z plus dz. I have a flux of CO2 coming in, and I have a flux of CO2 leaving. This could be CO2 in the gas phase, this could be CO2 in the bulk liquid phase, and then this would be the area of our film. We can write very quickly then that the accumulation of CO2 in this particular control volume is given by the moles per time of CO2, that's the accumulation, and the volume element here, dx, dy, dz, represents this volume element. The accumulation, of course, is governed by the flow in, a flux at a position z times an area, a flow out, a flux times a position z plus dz times an area, which means I can apply my famous chemical engineering principles, I can consider these terms, and I can rewrite that the accumulation of CO2 in my control volume, as shown here, is given by a derivative with respect to position. Derivative with respect to time is given by a derivative with respect to position. I need to invoke only one further step, namely to use Fick's law. Fick's law states that the flux of CO2 is given by a diffusion coefficient times a gradient with respect to position in space. I can insert this in for this value here and rewrite this equation, and I now have that the accumulation of CO2 in my volume element is given by a diffusion coefficient times the second derivative of the concentration of CO2 with respect to position. It turns out that differential equation can be solved pretty easily for this particular situation, because I recognize that at position z equals 0, the concentration is given by this particular number, and at position z equals L, the concentration is given by this particular number, and I use those boundary conditions, and one can easily solve then that the flux of CO2 is just given by a diffusion coefficient divided by the length times the gradient, as shown here, and you'll recognize that that's exactly the same as the rule that I invoked earlier on. So we've been able to derive that the flux is given by a mass transfer coefficient times the concentration driving force. Our conclusion then is that the reason we offset the equilibrium line to get a more accurate design is to account for the effects of mass transfer at each one of the stages in our absorption column. And we can either calculate those exactly if we know mass transfer coefficients and fluxes, or we can do it empirically by assuming that at each stage there's a certain efficiency. Now, the question then is, considering that we have mass transfer limitations, what might affect our design if there were chemical reactions also occurring in the fluids in our absorption column? Let's imagine, for example, that we have CO2 in the gas phase going to this film interface and then dissolving in a solution where there's a chemical component B in thermodynamic and chemical equilibrium, as shown here. So what are the consequences if these two steps, the fusion, the solution of CO2 in the film, and the reaction of CO2 component B, are governed by the equilibrium constant that you remember from chemistry, namely the concentration of products divided by the concentration of reactants gives you the equilibrium coefficient, as I've shown here. I can use these equilibrium constants to calculate the total amount of CO2 that is captured this chemical species here. And I can write then that the that's dissolved is given by this expression, which looks like a modified Henry coefficient times the partial pressure of CO2. And that modified Henry's coefficient is divided by the concentration of component B in this chemical equilibrium. In other words, if I increase B, I'll enhance the solubility of CO2 in the liquid phase, and thus am able to remove more CO2. This is a strategy used in the design of many for absorption. I can imagine one other situation, namely that the reaction in the liquid phase that occurs is not an equilibrium one, but in fact an irreversible reaction. The consequences for such an irreversible reaction. Well, again, I'm going to look at mass balance in this situation, but now, instead of just flow in minus flow out of my control volume, I also have a chemical reaction, a consumption term, in which the concentration in that volume element will decrease according to a rate constant and some rate law for the concentrations, a simple first order in B and CO2 as I've shown here. If I pursue my mass balance equations and work through the algebra, what I discover is that the flux of CO2 is given by a much more complicated expression than I had thought previously. However, I can look at the consequences of that by taking limits. Suppose, for example, that the diffusion of CO2 in the system is much, much more rapid than the chemical rate constant governed this expression here. Under those situations, the value for the flux in the system turns out to be almost exactly the same as if there were no chemical reaction. In other words, when diffusion is large, the chemical reaction appears to be irrelevant in the consideration of mass transfer. On the other hand, if the reaction rate is kept very large relative to the diffusion coefficient, as shown here, then the flux of CO2 across my interface in fact contains the rate constants and the diffusion coefficient. In other words, if chemical reactions are occurring in the liquid phase, the consequences for mass transfer and my design could be quite complicated, and that is the area of considerable design and analysis in chemical engineering. Having looked now at mass transfer and how chemical reactions affect the situation in an absorber, it's useful to return to our choice of solvents and ask, what are in fact the properties we need for the best solvent for adsorption? Following a paper that was published recently from some colleagues at the University of Texas at Austin, we recognize that the capacity of a solvent to take up CO2 is very important. The higher the capacity, the smaller the equipment we need to conduct our design, and hence the lower the capital cost for the process. We recognize these rate processes are important, and in particular the mass transfer coefficient is important in terms of minimizing the effects of mass transfer and their limitations on absorption at each particular plate. We also recognize that the reagents or the solvents we use must be robust against thermal decomposition in the temperatures associated with absorption and stripping. They must be resistant, of course, to oxygen and SOx that is appearing in the flue gas. And we certainly don't want those solvents to be volatile so that they slip or escape from our process and pose an environmental hazard. Furthermore, we also don't want those solvents to be very corrosive. In light of all these issues, it's useful to go back and consider amines again. And here's a diagram or a picture showing a family of many, many different amines that have been considered for absorption columns. I note that here is methanol monoethanolamine, a compound we discussed previously. And in the upper right, I'm showing piperazine, which is a new solvent being considered for absorption and strippers in CO2 capture. It's interesting to look at these systems on the following diagram, in which I show the effective rate coefficient or mass transfer coefficient associated with that particular solvent. And down here I show the capacity, that is how many moles of CO2 are associated with the salt per kilogram of solvent. And here are the primary amines, such as monoethanolamine, an effective solvent, as we have seen already in the literature since 1930s. But look over here and see where the piperazines are. They represent a great improvement in both rate and in capacity. And so, as you can see from this analysis, there is the possibility for research, design, and implementation of new amine solvents for the absorption of CO2 from flue gas. Okay, are there any questions about this particular video? I know there were some intense technical details. Those of you that are not engineers or quantitatively inclined might have been a little bit bored, but hopefully you recognize that moving molecules across these interfaces is what the absorption design is all about, and of course the sustainability and chemistry of the solvents is also very important. So let's return to our so the formation of carbamates turns out to be a critical part of all these amine processes. And if you examine what does that look like on a power plant. So here is a pilot plant from my colleagues at the University of Texas at Austin. This represents the absorption column right here. And over here, hidden behind the framework, is the stripping column. And the typical size of a unit like this is on the order of 20 by 20 by 20 meters. On a coal-fired power plant, that represents a 15% increase in the use of land area in order to use the absorption column. But perhaps most alarming is that you need 20% of the available power from the plant in order to accomplish this. And the reason absorption is such a difficult process is because you have to heat these solvents to get the CO2 back off again so that you can transport it and put it underground. In a sense, absorption is a frustrating process because inevitably you wind up boiling solvents in order to get the CO2 off. And so you're taking steam from the power plant to do that. So this is, but there is opportunity, and pushing this number down is where, for example, the piperazine solvents are going. And what is the melting point of piperazine, did we find? 102 degrees C is the melting point. It's a solution in water. Yeah, that's how it's used. So, okay, the absorption summary. It's proven technology that works. It's continuous. It's scalable. It's available. You can buy it today. It does suffer from these excessive energy and capital penalties. And we can do better and get closer to the thermodynamic energy minimum if we operate close to equilibrium, if we use clever engineering in the design of the unit, and of course choose the right kinds of solvents. And I've emphasized mainly this last point. So that concludes our section on absorption as a scheme for conducting carbon capture. And now we're going to switch to adsorption as our next topic. And if you'll let me just pull this up. We will have a break, but not right just yet. Okay. Yes, please ask. Yeah.
We have discussed this thing. Then we talk about interfacial layer and the small area itself. The same thing goes over here with the CO2, because I have never read about the CO2 absorption into liquids. Again, we have a liquid resistance. We have sometimes a gas resistance, depending upon liquid. So is it?
So the gas resistance is negligible for these, and if we design the solvents correctly, then the mass transfer rates for CO2 into that liquid phase are pretty rapid. But if we don't pay attention to that, so for example, water is the worst case because the liquid phase resistance is very large. And so mass transfer is a serious limitation.
Liquid film? Like
Yes. Yes, in both cases.
So both are poorly soluble gases in water.
Yes.
So both.
Yes.
Oxygen as well as the CO2.
As well as CO2. And you're familiar with oxygen because of wastewater treatment?
Yeah.
Of course. Yes, thank you. Are you guys ready? Okay, so let's turn and talk about adsorption now. Again, we're focusing on post-combustion capture. And we're now going to look at the adsorption process. This is different. The absorption was talking about mass transfer between a gas and a liquid and the chemistry associated with designing solvents. In adsorption, we're talking about mass transfer between a gas and a solid surface. And that's a critical difference, and it changes virtually everything about these particular processes. So in absorption, we're talking about liquids. In adsorption, we're talking about solids. So now we have to ask, what does an adsorption system look like? What makes for a good adsorption system? So in the case of absorption, we had all these attributes. The Henry's law coefficient, that was the equilibrium thermodynamics. Energy required, good solvent, contact area, avoiding degradation, and so forth and so on. And with the adsorption then, we still have Henry's law. It'll still be a linear relationship between the amount of CO2 in the vapor phase and the amount of CO2 on the solid surface. We also have a strong temperature and pressure dependence, and we'll come back to why in a minute. We also are going to require energy to regenerate. Rather than boil water, we're going to have to heat a solid to pop the CO2 off again. And we need something that has high capacity. We need high surface area. It has to be stable. And we have to optimize these systems so as to minimize the parasitic energy from the power plant. And so it turns out for adsorption, you can also do these graphical analyses, and hence their importance. Let's take a walk through what adsorption looks like in a cartoon sense. So here I have gas molecules. Here I have frustration of Professor Reimer with his mouse. We'll deal with that in the break. Empty sites on the surface. A solid surface is the gray area, and there's an occupied site. And the adsorption process really looks at overcoming adsorbate interactions in the gas phase and having stronger adsorbate surface interactions, either strong or weak interactions. And we have some pores in the material in which CO2 could form a liquid phase. And so now the question is, how are we going to regenerate this? Are we going to increase the temperature of the solid particle, or are we going to decrease the partial pressure so that the CO2 desorbs from these particular surfaces? So what kind of adsorption materials exist, and how might we use them? The most famous of which is silica. You're familiar with that, as I mentioned before, from your electronic devices. Activated carbon is an adsorbent, but it's typically from the liquid phase. Those of you who wish to purify your water often pass it through activated carbon because the carbon absorbs many of the materials that make us sick. High surface area materials from the petroleum industry, the molecular sieves and zeolites are popular. And of course, even simple baking soda works as a good adsorbent for the gases inside of your refrigerator. Alumina, Al2O3, is another adsorption material. These are all very, very high surface area and very useful for adsorption. Zeolites are these elaborate, in some cases natural crystals. They're made of building blocks of something like SiO2, and they're tetrahedrally shaped, and they form these really elaborate structures where the pores inside of these materials for CO2 to adsorb are on the order of the size of a CO2 molecule. So they really have extraordinary surface areas. The interesting thing is that if you imagine all the possible combinations of the crystalline forming elements, there are millions and millions of structures possible, which is both an opportunity for designing materials for adsorption, and it also represents a challenge, because even the best graduate student is not going to synthesize a million materials in the course of their thesis. Another class of materials that are very exciting for carbon capture are so-called metal organic frameworks. They consist of these very elaborate structures. The yellow ball represents open space. Just to show you how much surface area is available in something in which zinc oxide tetrahedra are linked by a linker. This one is an aromatic unit with 2 carboxylic acids, and they form these really elegant and elaborate structures. And in fact, just recently, a particular metal organic framework that was appended with amines was shown to be an extraordinary material because it captures carbon at half the energy cost. And if we have time, I'll say more about that, because if you look very, very carefully at this list of authors of the Nature paper, you'll see my name right there. So how much surface area is available in some of these materials? So here I have carbon, and here I have a molecular sieve or a zeolite. In the activated carbon, I'll have 1,500 meters squared per gram. And in this particular bottle, I have 12,000 meters squared surface. So to put some reality on that, let's take a typical cricket pitch and recognize the surface area is about 60 square meters. So this particular bottle has the equivalent of 212 cricket pitches, and this one 432 pitches. So these materials are really quite extraordinary in terms of their surface area. And if the CO2 is absorbing on the surface, then this is exactly what we're looking for. So now that's an introduction to the kind of materials, and now we have to ask what are the kinds of processes that are going to be needed in order to regenerate and to do these adsorptions. So this is a perfect time. We have to have a little shorter break this time because we have to end at 3:30. So it's at exactly 3 o'clock, I'm going to start talking again. That gives you only 6 minutes, and I'm sorry for that, but I'll see you in 6 minutes.